Hello everyone, welcome back to my tutorial. Today we are diving into something really exciting and important in the world of computer vision, DeepSORT, which stands for Simple Online and Real-Time Tracking with a Deep Association Metric. So, what exactly is DeepSORT? Well, imagine you are watching a crowded street from a security camera. You see people walking around, some disappearing behind camera and other coming back into view. Now, your job is to keep track of each person to know what the person who disappeared behind that car is the same person who came out on the other side. That's essentially what multiple object tracking is all about. It's like giving each object in a video its own unique ID and making sure we don't lose track of who is who. So, this is incredibly important in so many real world applications. Think about surveillance system in airports, autonomous car that needs to track credits, people and other vehicles, or even sports analytics where we track player throughout a game. The ability of constantly identifying and follow object is crucial for these systems to work properly. Now, before DeepSort came along, researchers were struggling with a major problem. The earlier tracking method, especially the original sort algorithm, had this annoying habit of losing track of objects. Imagine you are following someone in a crowd. They disappear behind a pillar for a few seconds, and when they came back out, you think they are completely different person. That exactly what was happening. These systems were experiencing what we call identity switches, where they lose track of who is who. Today we are going to break down the research paper that solved this problem and revolutionized object tracking. We will understand the clever technique that the author used, look at their result, and at the end I will show you how to implement this yourself. All right, let's dive into the research paper. The first thing we need to understand is the context of this work. Multiple object tracking has been around for quite some time, but it really took off with the rise of tracking by detection method. Now, what does tracking by detection mean? Think of it like instead of trying to track objects from the very first frame, we first detect all objects in each frame and then we try to connect these detections across frame. It's like taking snapshot of a room every second and then trying to figure out which person in snapshot 2 is the same as the person in snapshot 1. Before deep sort, there was the original sort algorithm introduced in 2016. Sort was actually pretty good. It was fast, simple, and worked in real time, but it had one major weakness. The biggest issue with sort was frequent identity switches. Let me explain this with a simple example. Imagine you are trying to track two people walking in a hallway. Imagine person A is wearing a red shirt, person B is wearing a blue shirt. They are walking towards each other, and for a moment they overlap. One person temporarily blocks the other from camera view. Now, when they separate and both become visible again, sort would sometimes get confused and think that the person in red shirt is actually person B and the person in blue shirt is person A. It's basically swapped their identities. This happened because sort only looked at motion information. It tried to predict where object would be based on their previous movement, but it completely ignored what the objects actually looked like. The technical term for this is that the sort relied solely on bounding boxes overlap using something called intersection over union or IOU. Think of IOU as a measure of how much two rectangles overlap. If they overlap a lot, the system assumes they are the same object. But when objects get occluded, that means blocked from view. This approach fails miserably. So, so how did the Deep Sort author solve this? They came up with a brilliant idea. Why don't we teach the system to remember what objects look like? This is where the deep sort come from. They use deep learning to give the tracking system of visual memory. Their approach combined two types of information. First, motion information. They kept the good part of sort, the Kalman filter and the Hungarian algorithm. Now, a filter is like smart predictor that say based on where this object was, how fast it was moving, here where I think it would be next. The Hungarian algorithm is like a matchmaker that pairs prediction with actual detection in most optimal way. Second, appearance information. This is the game changer. They added a CNN that is a type of deep learning model that's really good at understanding image. This CNN looks at each detected object and create what we call an appearance descriptor. Think of it uh, as a unique fingerprint for how that object look. The CNN they use is pretty sophisticated. Its wide residual network are a type of neural network architecture that really good at learning complex pattern. It helps to describe what the object look like. Maybe some numbers represent color, other represent shape, texture, and so on. Here's the clever part. For each object being tricked, the system remembers the last 100 appearance descriptor. It's like having a photo album for each person you are tracking. When a new detection comes in, the system look at the new detection and compare it with all the photo album to see which one matches best. So, how this fix the previous problem? The combination of motion and appearance information is like having both a GPS and your eyes when you are trying to find someone in a crowd. The GPS motion prediction tells you roughly where they should be, but your eyes appearance feature confirm that you are looking at the right person. When objects get occluded, remember that mean blocked from view, the motion prediction became unreliable, but the appearance feature remains consistent. So the object reappears, the system can say, here I remember what this person looked like and currently maintain their identity. The author also introduced something called a matching cascade algorithm. Instead of trying to solve everything at once, they prioritize track based on their age. Think of it like if you have been successfully tracking someone for a long time, they're probably more confident about who they are compared to someone you just started tracking. So the system gives priority to these more established tracks. Let's see the numbers. The author tested their method on something called MOT16 benchmark. This is like standardized test for tracking algorithm. They use several metrics to measure performance. DeepSORT achieved 61.4% MOTA compared to SORT's 59.8%. In identity switches, this was the big win. Remember, this was the main problem they were trying to solve. DeepSORT reduced identity switches by 45% from uh, now. What about processing speed? Despite all this additional complexity, DeepSORT still runs at 40 Hz, means it can process 40 frames per second, which is more than enough for real-time application. The benefits are pretty clear. First, you get much more reliable tracking. 45% fewer identity switches means your system is much less likely to get confused about who is who. Second, it handles occlusion much better. Third, it maintains real-time performance, so you can actually use it in practical application. Limitation, let's be honest about limitation two. First, you need a decent GPU to run this in real time because of CNN component. Second, it does produce more false positives. Sometimes it's a bit too eager to maintain track. Third, the CNN was trained specifically on people, so it might not work on other tracking objects like car without retraining. So, from my perspective, from a practical standpoint, deep sort is more of an intelligent evolution rather than a revolutionary breakthrough. The author were smart. They took what worked from sort and added the missing piece, visual memory, which solved a real problem that engineers were facing. This 45% reduction in identity switches is impressive and addresses a real-world need. However, the approach is fundamentally incremental. It combines existing techniques rather than introducing completely new algorithms. But sometimes that's exactly what the field needs, a practical solution that works. And there you have it. We have covered the complete DeepSort research paper and problem it solved. DeepSort shows that sometimes the best solution comes from combining different approaches intelligently. By adding visual memory to memory-based tracking, they created a system that much more robust and reliable. Uh, the key takeaway here is that appearance information is crucial for robust tracking. When motion prediction fail, having a visual memory of what object look like can save the day. So, in next part of this tutorial, we are going to dive into the actual code implementation. Let's see how you can implement DeepSort on your own. First, we start by installing required libraries. We have to install Ultralytic for object detection as we are going to use YOLO and Deep Sort Real Time. It's a library through which you can perform deep sort with few code. So we just have to run this code now. Now in deep sort, I'm using an embedder, which is a re-identification means a CNN which help in the identification of object. So this is I'm going to use the clip dot get. Now, in our next step, I'm creating a helper function. This function help me download sample video which I am going to use in this tutorial and visualize it in the notebook. Now, let's come to our main function. Deep sort. First, we import YOLO from Ultralytics, and then from Deep Sort real time, from Deep Sort tracker, we import Deep Sort. Then we import CV2 OS and a random to generate random color for each bounding boxes. Now, in Deep Sort algorithm, I'm providing with a model YOLO 11x. Then uh, here, as you can see, I initialize deep sort tracker. This tracker has a maximum age argument, means how much frame it will look before predicting the next frame, how much objects are required to start the tracking, means minimum number of objects after the tracking started is two, and then a embedder, which is a re-identification identity, which helps me extract features from object to keep track of it, which is clip VIT I'm using. And these are arguments you will need it for the deep sort. Now, as you can see, you are taking frames by frame and then providing frames to our model. And then for each detection, I am appending that value to detection list. And then this is the main code for deep sort. Using deep sort tracker, I am updating tracker based on its detection and frame, and taking that detection tracker is confirmed. I am drawing bounding boxes using this part of code, and then I am providing with each ID. The ID is already provided by the tracker algorithm. Then I am saving this into a video format. Now let's run this code. Let's track people first. This is the sample video I'm going to implement in this tutorial. This is a video of two people jogging. So it's a really simple video and a very much easy tracking video for a tractor. Let's implement deep sorting. You have seen the result of deep sort on this video. As you see, it worked very great or on these type of video where object is moving in a linear path. Now let's take an example of another video. Let's track plane. Now let's see the sample video I'm using. This is a video of multiple planes flying across sky. As you can see, these are traveling in a curved path, which make it harder for an object tracker to track it. Let's see the result of deep sort on it. As you can see, I'm providing with the part of the video and the output name and the target class, which is 4. 4 is the target class of plane in YOLO. Let's run this code. As you have now seen the result of deep sort on plane, it was a pretty good result. As you know that the plane has been very much clearly detected and it was the right identity provided to each object. Now let's see the edge cases of deep sort. This is a video I'm going to use. In this video, you can see the car is moving in a straight line, but the problem with it is that car, which is the object here, is becoming bigger by every frame, which make it difficult for tracker to detect, like Kalman filter to predict is the same as previous objects. You will see what will happen in this type of video. Let's see the inference of deep shot on this video. As you seen in the inference video, the result was not pretty much good. The object tracking was very bad and the identity kept switching. This was the edge cases or the limitation of Kalman filter which has been used in deep sort. It also failed to recognize the same object which is moving forward in different frame due to the limitation of feature extraction. With this, our tutorial on DeepSort is over. To learn more, you can check our Git repository where you can find every model's Jupyter notebook, its blog, and YouTube video related to it. There you can find every model related to computer vision in greater detail and how you can implement it yourself.